All right, let's take a look at our next reaction type, which is a condensation reaction. There's a couple condensation reactions we're going to look at. One, as you can see here, is esterification, the formation of an ester. What a condensation reaction involves is the combining of two larger molecules with the removal of a water molecule. So for esterification, formation of an ester, the reaction involves a primary alcohol. So it's got to be primary alcohol. Primary alcohol with a carboxylic acid. So let me drop some structural formulas and we'll see how this reaction occurs. So again, R is just a carbon or many carbons. So here's our acid. And here is our alcohol. And this reaction usually occurs in the presence of concentrated sulfuric acid. So I'll put that up here. So concentrated sulfuric acid. All right, so what happens is the hydrogen from the hydroxyl group of the alcohol and the hydroxyl group from the carboxylic acid make the water, and then we have a bond formed between this carbon and this oxygen. And so what we end up with is, and maybe I should put an R prime here. So we have R over here and R prime just so we can tell the difference. So we have our organic products and we have the formation of water. So in fact, let's do an actual example. I'm going to erase this. You can write this maybe towards the bottom. Yeah, we'll do some examples in just a second in that space. I have some other examples to do there as well, but we'll do those later. So let's just continue with the notes and then we'll do a couple examples. Esters, or it says these types of compounds, esters are used as flavoring agents, artificial smells or odors, perfumes, and solvents. So many of the artificial smells and flavors we get in foods come from some sort of ester. Let's take a look at some examples of actual esterification reactions. All right, let's write the equation for the reaction between propanoic acid and ethanol. So again, we have a primary alcohol, carboxylic acid. Go ahead and pause the video and write that equation just like I did with the example. Here's what we end up with. Again, we have our water comes from there. We have a covalent bond that forms between this carbon and this oxygen. And we kind of talked about it with naming esters. And I think I introduced this. The alcohol goes first in the name. So this was ethanol. And then the carboxylic acid goes second. So that's the first part of the name. This is the second part of the name. And so what is this ester called? Well, our alcohol was ethanol. So that's ethyl. And then our acid was propanoic acid. So this is ethyl propanoate. And then, of course, we get some water produced there as well. We're going to do some more examples later on, but after we get to the polymerization section in the notes. So just save that room there for later for more examples. I recently introduced amides, and so let's take a look at this one. An amide involves a reaction between, once again, an organic acid, a carboxylic acid, but instead of a primary alcohol like what we just saw, this time we have a primary amine. So let's take a look at a generic equation. So we have our carboxylic acid, and we have our primary amine. Maybe best to show this functional group this way, just so again we can see the formation of the water. So we end up with hydroxyl group from the acid and one of the hydrogens from the amino group forming our water. And then our product looks like this. That's an R. Let me try that again. Look kind of weird. So we end up with something like that, along with, of course, our inorganic product, water. So this type of bond is what forms between amino acids in a polypeptide. So this bond is known as a peptide bond. And the product that forms between two amino acids is called a dipeptide. If you had a bunch of amino acids bonded to each other in this way, we would call that a polypeptide. So just some additional information put into context where we see the formation of these bonds. So this is a peptide bond. Again, notice we have an acid and an amino group. And so, of course, the acid of one amino acid and the amino group of another amino acid combine to make our dipeptide or polypeptide, and we get some water produced as well. And once again, we'll see some examples of this type of bond formation with some polymers later on, so we'll just pause on the examples for now. All right, next up, I think I went a little too far. We have electrophilic substitution reactions with benzene. So we saw earlier electrophilic addition reactions with alkenes. We saw nucleophilic substitution reactions with halogenoalkanes. This time we have an electrophilic substitution reaction with benzene. So remember that even though benzene has, I did air quotes here, 3 double bonds, it is not your typical alkene that will undergo addition reactions, but benzene will undergo some substitution reactions. So again, just to review the term electrophile. An electrophile is an electron deficient species that can accept electron pairs from a nucleophile. And because of that, these are Lewis acids. So the example that you need to know involves the nitration of benzene. So adding the nitro functional group, or actually it's not really adding, we're substituting nitro functional group to benzene ring. So let's take a look at the overall equation for the reaction, and then we'll look at the mechanism. So we'll start with the line structure for benzene. So remember, chemical formula for benzene is C6H6. So every carbon in the ring has 3 bonds already and is bonded to just 1 hydrogen. So anytime we have a substitution reaction involving benzene, we are substituting something for a hydrogen. So in this case, the reaction involves actually a couple acids. So we have nitric acid. This reaction is catalyzed by concentrated sulfuric acid. And we also have to carry this out at 50 degrees Celsius. And then our product is our substituted benzene. This time we have nitrobenzene that's produced along with water. So let's start off with the production of our electrophile, which involves the protonation of nitric acid. So here's where the sulfuric acid is important. The nitric acid is going to be protonated. It's going to gain a proton. So let me draw that and show you what that looks like. All right, so the sulfuric acid is going to protonate the nitric acid. This step is reversible. And so what we end up with is something like this. So maybe I'll color coordinate it. So one of these hydrogens from sulfuric acid is used to protonate the nitric acid. So we have one of the lone pairs of electrons on the oxygen that forms the covalent bond with hydrogen. This gives the oxygen a positive charge. And because of that, then these electrons here are going to go to the oxygen to produce our leaving group, that's called, which is water. And then we have a lone pair of electrons on this oxygen, which are going to go there. And so we end up with our product. Again, this is a reversible step. And we get the formation of our electrophile, which is called nitronium. I'm going to write it this way. and this has a positive charge. Let me add our other products as well. So in this step, we'd also make HSO4 minus. And then again, I just want to show the formula of this. This is NO2 plus, called nitronium ion, which is our electrophile. So let's go over that one more time. So our first step is the protonation of the nitric acid. So one of the hydrogens from the sulfuric acid goes to this oxygen. So the covalent bond forms using this pair of electrons. And that gives oxygen here a positive charge. So remember, this hydroxyl group, if you will, it's not really a hydroxyl group technically, but a hydroxyl group on the nitric acid gains an H plus, so develops a positive charge. This pair of electrons here then goes to just the oxygen, and that produces our water. So I'm going to circle that. There's our water. Of course, we end up also, after the protonation of the nitric acid, with HSO4 minus ion. These electrons here from one of the lone pairs of electrons on oxygen will form a double bond with nitrogen. We get our water leaving group, and we get our nitronium ion, a positive charge, which means it is susceptible to attack from electrons. And so that's what's going to happen next. We have a reaction with the nitronium ion and benzene. All right, so let's take a look at that step. So again, we have some delocalized pi electrons, and two of those electrons are going to be used to form a covalent bond with the nitronium ion. So we have electrons, one of the pairs of delocalized pi electrons is going to grab onto the nitronium ion, and we're going to form an intermediate. And that intermediate happens to have both hydrogen and the nitro group bonded to a carbon. So I'm going to show it like this. Now, something that's interesting to note here is that we have lost one of our pairs of electrons that makes up the pi bond. And so what we usually do is we put kind of a dashed line in between there instead of a circle, and a plus inside of there. So again, we've added a positive ion to this neutral molecule benzene, and so now we've made this positive intermediate. So technically that positive charge resides on this carbon here because that carbon has bonded to a positive ion, but we can just put a plus sign inside the ring. The next part involves a regeneration of our sulfuric acid catalyst. So recall that we had HSO4 minus from that previous step, the protonation of the nitric acid. And so what's going to happen is, technically, again, it is a lone pair of electrons on one of these oxygens that grabs onto the hydrogen, forms a bond between oxygen and hydrogen, and then we're left with this pair of electrons here, which then goes back into our delocalized pi bond ring, if you will. So our three delocalized pairs of electrons. And so what we end up with then are our products. So we have free formation of our sulfuric acid catalyst, and then our organic product, of course, is nitrobenzene. And this nitrobenzene, by the way, appears as a yellow looking oil, kind of a viscous liquid that is yellow in color. All right, changing gears quite a bit here. Let's take a look at oxidation reactions involving alcohols. And what you need to know is the reaction that occurs between an alcohol and the oxidizing agent potassium dichromate. Now, it should be noted, you do have to know this, that dichromate in solution is orange, and it reduces to chromium 3, which is green in color. All right, so what kind of product we get from the oxidation of an alcohol depends on the type of alcohol. All right, so let's take a look at oxidation of primary alcohols. Remember that in a primary alcohol, the hydroxyl group is attached to a carbon with two hydrogen atoms attached to it, or the carbon that the hydroxyl group is attached to is bonded to one other carbon. So ethanol or 1-propanol or 1-butanol, those will all be examples of primary alcohols. This type of alcohol is easily oxidized to an aldehyde. You can further oxidize it to a carboxylic acid if you use a process known as reflux. If you would like to just get the aldehyde, then we just want to oxidize the alcohol to the aldehyde using a process called distillation. Um, that plus O, by the way, in brackets means that oxidation is occurring. In fact, usually the plus is outside of the brackets. Let me fix that. There we go, that looks better. We can see a picture of both of these apparati on page 492 in your textbook. So we'll start with 492 at the top. That is distillation, a process where you heat up a mixture. The more volatile substance will evaporate first. You can run that through a condenser. So that's the tubing, glass tubing with the rubber hoses attached to that. You have water running through there. That will cool down the vapor and condense it. And if you do so in the presence of, say, potassium dichromate or even potassium permanganate and other oxidizing agents, you would produce the aldehyde. Below that, and kind of towards the bottom of the page, we have a reflux setup. Same idea. You heat up a mixture. The more volatile components will evaporate more readily. That will go up into your condenser, so that's vapor will condense back into a liquid. But instead of going into a separate container like in distillation, it's going to fall back down into your glassware, your mixture that you're heating up. And this will allow for further oxidation. So if you don't let the aldehyde oxidize anymore, you get the aldehyde. If you take the aldehyde and further oxidize it using reflux, then you can get the carboxylic acid. So let's take a look at an example. I'll just use a generic equation. Again, this can be ethanol or 1-propanol or 1-butanol. And so if we take this and heat it up in the mixture, or sorry, in the presence rather, potassium dichromate, we are going to get the aldehyde. And if we take that aldehyde and further expose it to the potassium dichromate under reflux, if we heat it up under reflux, then we'll get the carboxylic acid. Whoops. I was going to show trigonal planar geometry, but I haven't on the other, so we'll just leave it like that. So take your primary alcohol, heat it under reflux. It'll initially form the aldehyde. You can continue to oxidize that aldehyde into a carboxylic acid. Or, I suppose, another reaction that might be important to know is how we can take an aldehyde and convert it to a carboxylic acid. That would be via oxidation. So you can oxidize a primary alcohol to an aldehyde. You can oxidize an aldehyde to a carboxylic acid. And again, usually we do so using either potassium dichromates, could also use potassium permanganate, which is another strong oxidizing agent. Don't forget our inorganic product of chromium-3, which again is green in color. So we see a visible change occur. Potassium dichromate is orange. And then when it has been reduced, we end up with green chromium-3. All right, so let's just look. Probably should have done just the aldehyde first, but that's okay. So take a primary alcohol and heat it up under distillation. This time I'm going to show it a little different. Instead of putting the dichromate formula or permanganate. I'm just going to put that generic symbol. So we could write it that way, or we could just put this way as well. And if we don't have enough room over the arrow, we can write it under the arrow. So we can mix this with an oxidizing agent and heat it up. And in this case, we will get, of course, just the aldehyde. And along with our, again, chromium 3 ion. All right, so how about oxidation of a secondary alcohol? So remember, in the primary alcohol, the hydroxyl group is on the end, and you form on the end a carbonyl carbon, which will give you either an aldehyde or carboxylic acid. Well, in a secondary alcohol, the hydroxyl group is not at the end, so you're forming a carbonyl carbon somewhere not on the end. And so this time, instead of forming an aldehyde or a carboxylic acid, we're forming a ketone. So secondary alcohol, the hydroxyl group is bonded to a carbon that is bonded to one hydrogen, or a better way of looking at it, that carbon is bonded to two other carbons, hence the term secondary alcohol. So let's take a look at the equation involving a secondary alcohol. So we could take something, well, it doesn't really matter what it is, so we'll do this. So this could be 2-propanol, as what's shown in your textbook. So if we take this and heat it under reflux, we'll form our product. So of course, not forget our oxidizing agent. I snuck that in there. So oxidizing agents such as dichromates, and we're going to heat this up under reflux. And so what we're going to end up with is this product, along with water this time. So we get a ketone. So in the example in your book, we have 2-propanol, and if we mix that with some potassium dichromate and heat it under reflux, we will oxidize that alcohol to a ketone, in this case, propanone. So same as before, of course, and we get our chromium 3 product if we are using dichromate as an oxidizing agent. May be helpful, or maybe good to know, that if you use permanganate, the reduced form of permanganate is manganese 2. So permanganate is dark purple in solution, manganese 2 is pink in solution. All right, how about tertiary alcohols? So again, in a tertiary alcohol, the hydroxyl group is bonded to a carbon that has no hydrogens bonded to it. Why? Because it is bonded to 3 other carbons, hence tertiary alcohol. Interestingly, if you take a tertiary alcohol and mix it with an oxidizing agent and heat it up, this will not be easily oxidized to anything. And so we're going to say no reaction here occurs. So cannot oxidize a tertiary alcohol using an oxidizing agent and heating it up, just not going to happen. I think that's a good place to stop. Next time, we will kind of go in the opposite direction, where we'll take substances and reduce them. So we'll look at a number of different reduction reactions. And of course, one of them involving ketones and aldehydes and carboxylic acids, kind of the opposite of what we saw here, where we were forming those substances. Right, thanks for watching. See you next time.